Thermistors. The name thermistor is a shortening of the words thermally sensitive resistor. Thermistors are the temperature-dependent resistors. Their resistance value changes rapidly with temperature. They are mainly the oxides of manganese and nickel. So a thermistor is completely different from a filament wire in terms of the graph with R against T, because for a filament wire, the graph of R against T is that when you increase T, the R increases. So for a filament lamp or filament wire, as you increase the temperature, the resistance will increase. However, for a thermistor, as the temperature increases, the resistance decreases. So filament lamp, positive ions vibrate because you're giving it energy. The electrons traveling collide and the resistance increases. So because you're giving it energy, kinetic energy, you're increasing the randomness. And also because the electrons are moving, the charges are moving, electrons are moving, they are, in quotes, colliding with the positive ions, and so therefore the resistance increases. However, for the thermistor, as the temperature increases, the number density of charge carriers increases. So that is the electrons. As the temperature increases in the thermistor, the number density of charge carriers increases. Right, a negative temperature coefficient. This means that as you increase the temperature, the resistance decreases. So this is a inversely proportional relationship. So again, as temperature increases, the electron density increases. Free electrons are released as temperature increases. Current increases as energy is supplied to the semiconductor. Resistance decreases as a result. There is something called a positive temperature coefficient. So what this means is that as you increase temperature, resistance increases. At low temperatures, its resistance is large, thousands of ohms. So that means that there is very little current. At high temperatures, its resistance is low, so like tens of ohms. Very little current will flow when it is cold. This means that its resistance increases as temperature falls. So the diagram in the circuit for a thermistor is the bottom left. So it looks like a resistor, and you have a diagonal line going through it with, it looks like a lever. So you've got diagonal line going through it, and then you've got that short piece of line connecting the edge of the resistor to the end of the diagonal line. So that is the diagram for a thermistor in a circuit. So what are they used for? Well, they're used for temperature sensors, kettles, heating devices, fire alarms, ovens, refrigerators, thermometers, digital thermometers, also using cars, automotive applications to measure temperature. So again, the NTC it stands for negative temperature coefficient. That is when, as you increase temperature, the resistance falls, making it particularly useful in a number of different areas. So you got a diagram of a negative temperature coefficient thermistor at the top right. So this is what the diagram looks like for a thermistor. If you look at the left hand side, the resistance decreases as you increase temperature, and we say that this is non-ohmic because it doesn't follow V equals IR, because V is proportional to I for ohmic conductors, where R stays constant. So this is non-ohmic because it is not a straight line. Light-dependent resistors, otherwise known as LDRs, follow the same principle as thermistors in the sense that they are made from a semiconductor material. The change in temperature varies as the resistance varies as you change temperature when the light is incident upon the material. What I mean is that for a thermistor, as the temperature changes, the resistance changes. But for an LDR, As the light intensity changes, then the resistance changes. So an LDR is about light intensity, thermistor is about temperature. So this should have been covered at GCSE, but just to recap, just to go a bit further, for a filament lamp, it is usually made of a metal, not a semiconductor. So the metal is a good conductor of heat and electricity at room temperature. So for a filament lamp, as you increase the current and as you increase temperature, then the positive ions will vibrate a lot more. This increases the resistance because the flow of electrons will be impeded, will be slowed down by the vibrations of the positive ions, by the collisions between the negative electrons and the positive ions. For thermistor, however, as you increase the current, the temperature also increases. And this decreases the resistance because now you're releasing the electrons. For a conductor, the electrons were already free, but for a semiconductor, you can think of the electrons being trapped. So you're providing the energy to the trapped electrons, making them free. So therefore, the number density of the charge carriers increases as you increase temperature and current for a thermistor. If you look at this slide, if you look at the top left where you got the IV characteristic of a thermistor, the gradient will increase. Now, because if you use the equation V equals IR, rearrange for R equals V over I. So if you were to work out the gradient of a IV characteristic or IV graph, that would give you 1 over R instead. To work out the resistance, you need to do the reciprocal of the gradient when you're doing the gradient of an IV characteristic. So, because the gradient is very high in the IV graph for a thermistor, that means that the resistance is low. So it's the inverse. Think of the opposite to the gradient. Yeah, so it's the opposite gradient of the IV graph. If you look at the bottom right, so again, this is like this graph here on the left. So on the right hand side, as you increase temperature, you decrease resistance. Now if you look at the gradient at the beginning of the graph, where the temperature is 0, quite close to 0, you have a very large resistance. But if you when you increase energy, when you increase the temperature, it starts to fall very steep. So it falls a large amount. So at the beginning, when it's at low temperatures, as you increase the temperature, you start to decrease the resistance at a large rate. Right, so just make sure you're able to rearrange the formula. R equals V over I, 1 over R equals I over V, because I over V means the gradient of the IV characteristic of a thermistor. This is talking about the conductors and insulators. So conductors have delocalized electrons because they have 1 electron in the valence shell or outer shell. Semiconductors, on the other hand, typically have 4 electrons in their valence shell. So metals are good conductors of electricity because they have 3 electrons that can move easily between atoms. Silicon crystals are not metallic. They are not metals because they have perfectly covalent bonds. They can't move around, so it is nearly an insulator. Very electricity will flow. However, you do need to do some doping. Doping means adding impurities or adding extra substances into the semiconductor. Right, so the diode right, so for a diode will conduct electricity easily, much more easily in one direction. So it is designed to flow in one direction. So in the opposite direction, it does conduct electricity, but we'll come. That is for another day. So a diode will conduct current in one direction much more easily. Now, if you remember that the definition of current is the rate of flow of charge, in this case, it's the flow of electrons from negative to positive. for diode, there's something called electrons and holes. Now, because silicon is a semiconductor, you need to do some doping in order to induce a current, let's just say. So, because it has 4 electrons in the outer shell, when you add, for example, boron is in group 3. So when you add an atom of boron into silicon, you will have a free space for the electrons. So you can think of, if you're adding boron to silicon, and you know that boron's in group 3, silicon is in group 4, you end up with an extra space for the electrons to flow. Alright, so what I mean is there are more holes. So in this case, because you've added an atom with that is in group 3 to a silicon which is in group 4, now there are more, so there are less electrons, right? Because you've added boron into silicon. So there are less electrons, meaning that there are more holes. Holes meaning more positive. And so therefore this is a p-type material. Now this would be, because now you have less electrons, this is a positive. This is a p-type because boron's in group 3. So therefore you have the overall, it is more positive. For an n-type, you would need to add, for example, phosphorus to silicon because phosphorus is in group 5, and phosphorus, because the atom for phosphorus has an extra electron compared to the silicon, it has more free electrons. So the n-type means that it has more free electrons, meaning more negative, and the p-type meaning that it has less electrons, meaning overall has more positive. Now the p-type would imply it has more positive charge, meaning that it has holes in the p-type, and the n-type, it has an excess of electrons. So if P is made more positive than N-type, that will be the forward bias. And the holes in the P-type material will go to the N-type material, and the electrons in the N-type material will go to the P-type material. Now there is a barrier between the P-type and the N-type. Let's go back to that later on. So for a diode, the symbol for a diode is on the right hand side. You've got a triangle and a line at the tip of the arrow, and for an LED, it is the symbol for a diode, but then you've got 2 arrows coming out of it that signals the light that is being released. So when the material conducts electricity, it emits light specific wavelength. This is an LED, light emitting diode. It is efficient, little energy is used up. They light up when there is a current, and so if it lights up, then that implies is a current. So for example, you can use diodes to detect if a current is flowing in the right direction. So this is the IV characteristic for a diode in the positive region. So if you look at 0, just after 0, the resistance is still quite high, but then the current will increase gradually. And then above a certain point, so for example for silicon, after above 0.7 volts, then the current will start to flow more freely because the resistance is a lot lower. So this is non-ohmic, meaning that it is not a straight line, this is a curve, it does not obey Ohm's law, it does not obey V equals IR, and the resistance of a diode is not constant. Right, this is a more complicated diagram for a diode, for IV characteristic for a diode. Now, the graph where it says point A, ignore the xenodiodes for the moment. The xenodiodes is beyond the scope of this this clip. So if you look at A, so at A, the resistance is very high. The diode does not conduct, in quotes. At B, the resistance starts to drop gradually, and that is when the current starts to flow, but at a slow pace. But then above a certain point for silicon, 0.7 volts, the resistance is very low, or small increases in V, above this point, there is very, very little resistance. So the definition of the threshold voltage at the top of the slide, the threshold voltage is the voltage where the diode has enough voltage to conduct a large amount of current through it. And if you look at the bottom left, different color LEDs have different thresholds. This is to do with the photoelectric effect. Now, the conventional current flow, if you follow the direction of the triangle where the tip is going towards the left, that will be the direction of the current flow, so from positive to negative. If you want to read about the Zener diode, it's here, but I'll just you can pause and read, but I'll move on. So this is for a filament lamp. So the filament lamp, you can think of the filament lamp as the inverse of the thermistor. So if I go back to the thermistor, so the thermistor looks like, what does it look like? It's a cubic. Let's just say it looks like a cubic graph. For a filament lamp, it looks more like an S. So as you increase the voltage, the current becomes less and less. That's why it looks like it's becoming more horizontal as you increase V. So a conductor which disobeys Ohm's law is said to be a non-ohmic conductor. So remember, V equals IR. It is a straight line where V is proportional to I and R is a constant. In this case, R is not a constant. So the filament has a high resistance when you increase current because it starts to heat up and it starts to glow. So this is what the IV characteristic of a filament lamp looks like. So again, if you look at 1 over R, because this is the gradient, as you increase V, the current will increase, but at a very small amount. So that implies that 1 over R is very low because the gradient has a small value, and then because you need to do the inverse of the gradient R becomes very high. So R, the resistance, is very high for a IV characteristic of a filament lamp. So the resistance of a filament lamp increases as the temperature of the filament increases. So the resistance does depend on temperature. Reversing the voltage, negative values on the graph reverses the direction of the electric current but does not change the shape of the curve. So because a filament lamp is just a metal, you can change the metal, you can swap the ends of a metal, or you can swap the polarity of the battery. However, for a diode, because you've got NP and PN, NP and PN, if you were to change it, it won't allow the current to flow. If you just ignore the if you just ignore the Zener diode properties, then yes, it would only flow in one direction. Alright, so if you look at the question, this is in the OCR book. Question 1. A thermistor is used in a thermostat in order to maintain a constant temperature inside a lorry delivering frozen goods. Describe how any changes in the temperature inside the lorry would affect the resistance of the thermistor. 1 mark. B. Suggest how the thermistor might be used to ensure the produce transported by the lorry is kept at a constant temperature. 2 marks. 2. Sketch a labeled graph to show how the resistance of a typical thermistor used inside an oven varies with temperature. Now, the temperature of an oven is around about 200 to 300 degrees Celsius. You should include typical values for the temperature and an explanation of why you selected these values. This is 3 marks. Alright, so the answers are here. Have a look at the answers. Let me move on to question 3. So for question 3, table 1 contains data collected using a thermistor in a water bath. The thermistor was connected to a 1.5 volt cell. Plot a graph of resistance against temperature for the thermistor. This is 5 marks. Variation of current with changing temperature. So you got temperature at the top row and then current in the thermistor in milliamps at the bottom row. Use your graph from question 3 to determine the resistance of the thermistor at A, -5 degrees and B, 25 degrees. Question 5. The thermistor used in question 3 is now used to measure the temperature in a water heater. the current in the thermistor was 45.2 milliamps, and the potential difference across it was 1.03 volts. Determine the temperature of the water heater, 3 marks. Now I have drawn a graph, but the graph is current against temperature. So this is the graph of current against temperature, but you need to draw a graph of resistance against temperature. So, I mean, you are perfectly allowed to use this graph to answer the questions, but you would need to draw a resistance against temperature graph. Alright, so the answers to questions 3, 4, and 5 are on the screen now. And also, just lastly, that V equals IR, this is Ohm's law. So anything that obeys Ohm's law, V equals IR, it will be a straight line. So if you look at the one on the left, V against I, the gradient of a graph where it says V against I will give you resistance. However, if you have IV, usually the IV characteristic, the gradient of that would be 1 over R. So to work out the resistance when you have an IV graph, it is the 1 over the gradient. So again, it is a straight line for an ohmic conductor because V equals IR, where V is proportional to I because the resistance is the same. For a thermistor, the resistance changes. For a filament lamp, the resistance changes.